I don't know about you, but today is going to be one of those, another one of those heavy duty days where you get to see a lot of examples of different integrals. Here is my list, my standard integrals. I'll try and keep them here as much as I can. And we're going to work through indefinite integrals and actually definite integrals as well. They've called the second half of the section the net change theorem, so let me just tell you what the heck that means. You know how when I normally do my guy, it's always above the x-axis because it's just easy to draw, but can't you have a curve that dips below the x-axis and above? So how do you find the area under the curve? Well, it's the integral from a to b of f of x dx. It's still antiderivative at b, take away antiderivative a. This fella here is sometimes called the net area. And so when you hear the word or you see the phrase net change theorem, they're not asking for anything different. They're just asking for this fella. But we have to realize that the area under the curve here is not a physical area. It's kind of this is positive, this is negative, this little bit is positive. So it's a net effect. I guess that's why they called it the net area, right? It's not the physical area, it's the net change or the net area. And so isn't it possible for this answer, this combined answer, to be zero? Couldn't you have the bit above cancelling out the bit below? And couldn't you have it positive? Yeah, you've had lots of them. Couldn't you even have it negative? So that's all I'm trying to say here. So as we go through these, don't talk yourself out of a right answer because it looks funny. Because you're going to get some where the answer is zero and you're going to say, but there is an area, I can see it on my calculator. But you're thinking physical area when you do that, or negative for that matter. Okay, so lots of different things to deal with, but today I'm going to focus much more on, well, I won't call them trig questions because it's unfair to them because they're not meant to trick you, but ones where they're not obvious, let's put it that way. And not obvious can come from all sorts of things. So I'm going to look at some trig situations. So we're going to look at integrals of trig functions that are not that obvious. I'm going to start with an obvious one. So this is just one I'm making up. Okay, what is the integral of a secant or a secant squared? Well, you should be able to find it over here, and to see the answer's tan. So this would be 3 tan theta plus c. Would you all agree that's a one-liner? The answer's over here. What are you talking about? Well, I'm not talking about that one, that's for sure. But suppose I did this to you. There is no tan squared theta here. I wish there was. If it was, it'd be a dead easy question. What we have to do here is we have to figure another way of writing tan squared. Trig identities. I know you didn't like trig identities when you got them the first time. You probably still don't like them, but they're important. Does anybody know a different version of tan squared, a trig identity that says what tan squared could be equal to? Oh, come on, go for it. If you're wrong, you're wrong. At least you had a shot at it. Tan squared.
Would it be 1 over cotangent squared?
It is 1 over cotangent squared, but 1 over cotangent squared is not on my list. So basically, you have to figure out tan squared in terms of one of these guys. That's the only guys in town.
Secant squared minus 1.
Correct. Are you just good at remembering, or did you look it up somewhere?
I have a sheet beside me that has all of these things written down.
Maybe everybody else should get a hold of that same sheet based on the amount of time it took one person to tell me that. Is that a standard sheet? Is that something you can do a PDF and send it to me, and I'll send it to everybody if you find it useful?
Yeah, let me see. I have the file still on my computer somewhere.
Okay, if you can do that, I will put that, once I get it, I'll put it in Canvas and you can have a look at it, because, okay, there's an infinite number of trig identities. Nobody's going to remember them all, although I hope you would remember the tan squared, secant squared combination. Now, once you've done that, the question does become a different question, in the sense it's made up of different pieces, although it's equivalent to that one, because that guy is now 3 tan theta and -3. What would the antiderivative of -3 be?
It'd be -3x, yeah.
No. But I know why you said
Okay,
that.
yeah.
Right? Whatever the variable happens to be in the question. So -3 becomes, in this case, -3 theta. If everything was x's, you would be perfectly right. It would have been -3x. Do you see where we're going today? Is that we're not giving you questions like yesterday where it was mostly algebra, wasn't it, right? Sometimes you had to FOIL things out or multiply or change square roots to cube roots, and they're all very important. So part of my focus today is on different issues. In this case, trig identities can help us out. So next fella I'm going to pick is a version of question 16. So this truly is one of the homework questions. It's a secant t, 3 secant t, 7 tan t, dt. So when you get questions like this, you should have a kind of a direction to go. I'm going to do this probably first, and then I'm going to see what happens. Or I'm going to do A, then B, then C. You've got to have a direction to go. What do you think would be a good move, even if you don't know the answer yet, to integrating that? Because it's no good the way it's written.
Multiply or like FOIL the secant.
Okay, that sounds to me like a good idea. And that's what I would do. Now, if you look really carefully, aren't those two guys good to go? So the integral of 3 secant squared is 3 tan. And 7 secant tan is just a secant. So 7 secant tan gets you 7 secants. Now, you see, that one, you needed an identity. This one, you needed to realize that if you distributed the secant, it became terms that you could get in my little trig list here, right? And that one up there is, it's good to go. So there's a whole spectrum of things with trig in them. Of course, that's not the only ones we can do. So here's another one, which is actually straight out of the homework. So the integral of 3 sine of 2x over the cosine of x dx. This one involves us recognizing that there's a different way of writing this. And it's it's a trig identity. You can call them all identities. The only guy that's in that list that really looks like it's changeable, if there is such a word, would you agree it's sine 2x? Everything else looks pretty basic. So has anybody got an idea of a different way to write the sine of 2x? called the double angle formula. The sine of 2x.
2 sine x cosine x.
And that now becomes 6 sine x cosine x over cosine x. Now, hopefully you see something really nice happening here. Can you see something really nice happening? Right, they cancel it. So what you in fact have got this is, if you think back to trig, remember you did not probably as much as we'd like, but there's only so much you can do anything, of taking trig expressions and simplifying them, or proving that identities was another way that they sometimes did this. Do you see how useful it is to have that as a skill, that you can take trig and manipulate it and change it and make it nicer? Because that guy is -6 cosine x. I'd say now he's done. So the original can't do it, converted it into an equivalent that I can integrate, and then you integrate. Any questions about that? Problem you're going to have is a lot of these questions are easy when you see me doing them, or someone else tells us how to do it. Oh yeah, that makes sense. But you need to have the, that makes sense bit in place. You have to be able to look at that and see how it's going to, turn out. Got anything else here in the trig world? Nothing particularly interesting going on here. Nope. I think that's I'm just scanning through because there's a lot of questions and I don't want to miss one. The integral. This is a version of 34. So it's the integral of the sine of theta. We'll stick a 3 at front, I guess. Plus another 3 sine of theta. Tan squared theta. All over secant squared theta d theta. The only difference is that they've got from 0 to pi upon 3, but you could change that anyway. That wouldn't be that's not really the big problem. Would you agree that is horrendous? There is no way in the world right now that I can integrate that. It doesn't even vaguely look like anything over here. But nonetheless, it's eventually going to look like pieces of these. I'll take, let's forget about the integral and the dx, so I don't have to do that. Let's just focus on simplifying the original expression. Has anybody got any ideas about just the basic strategy of what you might do to make this a little bit easier to deal with?
You could take the sine out of the 2 top terms.
Okay. While I'm at it, I might as well take the 3 as well then, right?
I think that's a trig identity.
You're right, it is. If the world was nice, what would you hope it was equal to, even if you couldn't find it?
Secant squared theta.
And it is. So Now you can cancel. Which means that ugly thing is actually just this thing. Do you see why trig identities or manipulating with trig functions is a skill that's worth it, at least in integration situations? That this horrible mess is actually just 3 sine theta when all is done at the end. Well, we all know how to integrate that, so I'm not going to finish it. How about this one? Version of 36. The only difference is they put numbers on it, but I'm just skipping those out. Cosecant t cotangent t dt. Since this one is pretty small, I'm just going to keep it inside the integral. Okay, that fella is not in my list. But we need to see if we can change it into something that is in my list. Where are we going this time? I give you a help here. If you've got an expression, one of the kind of typical techniques, doesn't work all the time, but it's at least worth a try, is to turn everything into sines and cosines and see where it goes. It's not guaranteed to work every question, but it can sometimes get you out of trouble. And sometimes it'll get you the right answer. It'll just take you twice as long. See that previous question, which is this one up here? See if I turned all of them into sines and cosines, you'll have to trust me this because I'm not going to do it. It'd take too long. But if I turned everything here into sines and cosines, can you trust me? It would still end up being 3 sine theta. It would just take you a lot more work before you got there. Right? So, what is a cosecant in terms of sines and cosines?
1 over sine.
What is a cotangent in terms of sines and cosines?
One over tangent.
That's true, but in terms of sines and cosines.
Sine over cosine.
Or, well, I hoped it was. That's what I'm thinking. Did they put the wrong question? If I've written the
Cosine
wrong
over
question?
sine.
Is that right? Right. That didn't work. I wonder if they've just put the thing wrong. I wonder if they've just that. Huh. Let me think about that one. I wonder if they meant this. Because if that had been the real question, it would have been 1 over sine over cosine. No, that wouldn't have worked either. Oh, that one's interesting. Oh, I know the answer. It's cosecant t with a minus. Yeah. Cosecant cotangent is negative cosecant plus c. That guy is actually a standard integral. Now you might say, well, how do you know that? Well, apart from the fact I forgot to write it down means I forgot about it. I'm glad I had the space there. If you differentiate this side, shouldn't you get that side? So you try differentiating in your own time, -1 over -1 over sine t, and I bet you'll end up with this guy. So this is basically just trust me, it works. So apologize for that one. The sine over cosine thing did not work. Did you notice that? That doesn't mean that the next time I do it, it will work. Unfortunately, that is every trig situation covered. I can't find any more. So we're now going to look at factoring situations. So suppose I wanted to do that integral. If it was over x, that would be much easier, right? We've done questions where it was over x, but it isn't over x. It's going to be x over -1 or whatever it is. You'll see other examples. And can I rewrite this question again? Because plus what I meant a minus. There we go. That's the order I wanted to do it. So forget that one. Can you factor anything in this expression? Can you factor anything here? Okay, what do you get? Factor x squared -1. What do you get?
X plus 1, x minus 1.
Do you see something really nice happening here? Can you see x plus 1's cancelling? What am I left with? The integral of x minus 1. And this I know how you do, because it's a power rule. So we are looking at questions now where you have to factor things so that you're able to cancel and then simplify. And the simplified guy should be something you know how to do. So I do not know how to integrate that, but would you agree if I algebraically convert it into this, its integral is pretty straightforward. Right? So that's the goal that we're going to be doing for this bunch of questions. So here is a version of 37. Now, I know you can factor t squared minus 1, right? I mean, it'd be t plus 1, t minus 1. I'm not saying that you couldn't do that, but let's not do that yet. Let's just leave it alone. Can you factor t to the 4 minus 1? And the answer is yes. It's not as common, but it is doable. Isn't it also a difference of squares, but a kind of bigger grown-up version? It's t squared plus 1 times t squared minus 1. Are you all happy that that's t to the 4 minus 1 being factored? Have you also noticed that by not doing anything to the t squared minus 1, I've made my life a little bit easier, because can't I just cancel those two, one on top and one in the bottom? So when I cancel this one with this one, I'm left with that. So this guy is actually that guy. But I don't mind that guy, because isn't that guy this one? So I can do its integral. It's an inverse tan of t plus c. Looking good? Where factoring can be your friend. Now, I don't know, you know, they'll put numbers like 0 and √3 here and you plug them in, but I'm not doing the number crunching one. I'm just doing the indefinite version of these. So I guess I should be putting a little asterisk on these. See what we can see. Nothing special going on there. Nothing that interesting going on here. We are getting pretty close to the end of these. I'm seeing if I can find another factor one, but nah, I think it's over. Okay, then I'll make one up. How about this one as our last one of this type? How about 2x plus 1 on the bottom and 2x squared plus 3x plus 1 on the top, you know, something like that. Then 2x plus 1, x plus 1 is the factor. That's what we get when we factor them. Then I can cancel these. And it's done. Well, almost done, I guess. That looks actually deja vu, like I did something like that a minute ago. Never mind. Okay, so we've looked at trig situations and we've looked at factoring situations. So what I'm going to do now is we're going to go to the homework on that section. And we're going to look at the start and the finish, hopefully. And with maybe one situation that I haven't covered, we should be able to do all the questions. So before I start on that, is there anything that we've gone over that you'd like me to talk about? I'll be pretty good with the ones we've done. Okay, so probably make this as big as I can get it.
I had a question on
Yes.
what we wrote at like the very beginning. I wasn't able to get the information there.
So right at the beginning, I go back to my first page. What you're talking about is probably in there. So let's see if we can get that guy for you. So guy from this list here.
It was the net change theorem.
Oh, the net change. Okay. That was my intro notes. You know, I should buy stocks on paper manufacturers. You have no idea how much paper I go through. So basically, the net change theorem isn't anything new. They're just a name to something we already have been doing. What I said is that we're looking for the area under the curve, and this is how you get it. But I'm just emphasizing now that the area under a curve, especially when the curve goes below the x-axis as well as above it, that area is not the physical area of these pieces. It's the net area or the net change, because these are positive values and this guy here is negative. So what I was saying is, look, it is possible, isn't it, to get the answer to one of these integrals to be 0. It doesn't mean there's no shape there. It just means the bit that's above is exactly the same size as the bit that's below the x-axis. And that's why it's called the net change. I would probably call it the net area, to be honest, but I'm not in charge of names. But maybe when I take over the world, I'll get to be in charge of names. That would be a good job. Okay, so we're going to look at, or at least talk through, as many of these guys as we can so that we can finish it today. So I was going to make this a little bit bigger. I don't know how big I can get it. That's as big, I think, as I can get it. Right, in question 1, it looks like there is no question except true or false. And it gives you an integral on the left, and it gives you the answer, what it should be. It's antiderivative on the right. And your job is to decide, is it true or false? And they even tell you how you're going to do it. You're going to prove something is the right answer by differentiation. What that means is, you see this guy here? If you differentiate him, if you get this guy here, you'll put true. If when you differentiate this guy, you don't get this guy, you do false. Now, if you were doing a test, can you imagine you were given the job of integrating something and you had an extra 5 minutes and you wanted to check it? Couldn't you take your answer and differentiate it? And if it was the same as the thing inside the integral, isn't that kind of proof you did it right? Yeah. Integral gives me answer. Derivative of answer should give me the integral, right? You know, they work in both ways. So that's what that's saying. Good luck differentiating that. I'd probably guess, because I'm lazy, I'd say true and then I'd say false. But when it's reasonable, you should do it. Would you agree this one is just a power rule? Move on. Power rule and what? A plus sign x. Oh, and remember your plus c. Okay, how would you tackle question 4? Don't need the answer, just how would you tackle it?
Convert the square root into a exponent.
Yeah, so call it x to the 1/5 and plus x to the negative 1/5 and do the power rule on it. I know they look ugly, but aren't they just a power rule with really ugly numbers? When you do question 5, isn't there a very good chance that your coefficients, right, the number in front of your powers, will be equally ugly? Sometimes you can't help that, right? You can try and make them pretty. That one's very simple. What fractional power will I turn that one into? I guess there's only 2 answers. One is right and one is wrong.
7/6.
That's the right way. Would you agree that's just a power rule with ugly fractions? Would you agree that's a power rule? What would you do in question 9 to get the answer?
Foil.
Yep, and it'd be a power rule. What would you do in 10?
Negative power of x from the denominator.
Okay, that would work. And you'd get, well, you'd end up with a 3/x and some x power. So you'd end up with a log and some power rules. Would you agree that is power rule, power rule? Do you recognize 8/x² plus 1? What's the antiderivative of 8/x² plus 1?
Is it a tangent? Is one of the
Almost not quite tangent, but very close to being a tangent. And don't say arc or I'll throw some at you.
I have it written down.
8 inverse tangent, that's how close you were. 8 inverse tangent. I don't think you said inverse. Hope you didn't.
I did not.
Okay. Would you agree that 12, oh, let's show you something on 12. 12 looks very innocuous. Like, how could I screw up 12? I could screw up 12 really easily. Watch what happens here. I have an e to the x, which is my friend. I very rarely screw up him. But this fella here, this guy gets you e to the x. This guy here is the problem. It's 1/4x. It might be helpful to write it as 1/4 1/x. Can you see why that might be a easier way to deal with it now? Because won't that get me 1/4 natural log of x add c? Right. You are now about to see all the different flavors of the wrong answer. The correct answer first. This one. Now versions of the wrong answer. Natural log of 4x. 4 times the natural log of 4x. 1/4 times the natural log of 4x. Can you see why that 4 just gets in the way, and then you try and figure a way of fixing it, none of which actually work? So that's a kind of one-off thing, right? But you know, it'll happen, right? Aren't you going to get 1/2x sometime? You know, and the same kind of thing's going to happen again. So I'm cool with that. Right, let's return. Okay. This will test your memory. What's the antiderivative of 4 to the power of x?
3x plus 4 to the x divided by the natural log of 4.
Yep, you nailed it. Okay, don't want the answer. Just tell me how you would approach this. What would you do algebraically in 14? Any suggestions? How could you start 14? Just what would you do? You get it closer to where it needs to be. Nothing?
You deal with the square first and see what
Yeah.
those two.
So do a 4 plus 3 brackets squared on the top and then r squared on the bottom. Foil it out, and then, you know, well, you can, that r squared on the bottom, you can deal with that 2 ways. You can bring it on the top and call it r to the -2, or you can split it into 3 fractions, all of which have an r squared on the bottom. That's how we do that one. 15 is a good to go. We've done 16. We've done 17. 18 is good to go. Would you agree that's just a sine of x plus 1/6 x squared, right? Nothing need to be done. Oh, and then they said, illustrate by graphing several members of the same family. Right, if you do this one, you will get sine x. I guess I'll put brackets on it because that's what they do. You get a sine x plus eventually 1/6 with an x squared. And then a plus big C, right? We're all happy with that. Now, what are they on about? Illustrate by graphing several members of the family. On your TI-80 4 or Desmos, whatever you do, sketch that guy. And then sketch that guy plus 1, sketch that guy plus 3, sketch that guy plus 5, sketch that guy minus 1, sketch that guy minus 3, and sketch that guy minus 5, right? So pick various numbers for C, plus and negative, and you get a whole family of questions. You see, that's what they did using -5, 0, 5s, and 10s. Or did it look like that when you did it? Or did it look like that when you did it? Or did it look like that? So one of those pictures is right. This one is baby. Would you agree this is just a definite integral now? Power rule. Big power rule. More power rule. Do the guy with the plus C. That's the indefinite integral. Then do it with numbers. That's the definite integral. Okay, what would you do in question 23? Don't need the answer, but just what would you do in 23?
Foiling.
Yeah. And then can you imagine after you foiled it, just be lots of power rules?
Yeah.
It'd be ugly, big, messy, whatever, but it's doable. Okay, what would you do in 24? What would you turn 1 over x squared into, for instance?
X to the -2.
Correct. And 4 over x cubed then would be?
4x to the -3.
Isn't that just a power rule with ugly negative numbers?
Yeah.
And remember style points?
Mhm.
Right. What are you going to do by 25? Oh, that's got you stumped. What are you going to do by 25?
Would you factor it?
Not sure what you mean by that. You could be right. Depends what you mean by it.
If you factor no, you would split the 3x squared plus 5x into 1 and then the over x and then split 1 over x as a second one, right?
Okay. Yes,
That we get rid of the x.
that would work. Now, very often you need to see things because when you just verbalize it, it doesn't, I'm not sure what you mean kind of thing, because I know what you mean, but I'm going to show you. I'm saying, darn it in space, I've got these windows all over the place. Go away, window. Don't need you. Right. So we'll forget about the numbers. That you can do later. There are 2 distinctly different methods, both work for doing this guy. The one that I believe you were describing to me is where you essentially split the original into 3 baby fractions. Now that one can cancel an x and you get 3x. This one cancels, you get 5, and this one I'm going to leave alone. Would you agree that we can integrate this power rule log? So that's how that one works. A slightly different approach to the same question. This guy here. You could bring it to the top and multiply through them by -1. And this guy times that guy gets you 3x. This guy times this guy gets you 5. And then you're left with a really awkward x to the -1 guy. Now we know x to the -1 is a special case. The power rule doesn't work with that because if you add 1 to the power, you end up trying to divide by 0. So what you would need to do if you went this second route is you need to realize that it's better to leave the last one as that. And you see, we can now get the answer. So that would be the strategies. Is that essentially the top one is what you were thinking about when you were describing it to me?
Yeah.
Right. Now there's, flavors of that technique. It doesn't mean you're wrong just because you've got a slightly different version, but it is cool. Right. 26. How about just foiling it out and then multiplying by t and getting the power rule? Does that seem a pretty straightforward one? Okay. Okay, what about 27? Don't think we actually did a 27, so that's kind of cool. What method would you use to do 27?
I would multiply 2 and 6u by u to the -1/2.
And it works really good if you do that, trust me. You end up with power rules with fractions, but that's it. So it works really good. Would you agree that's just 6 times the inverse tan of b? Nothing to do with that one. So can you notice that some questions you have to do a lot and some questions the answer's in front of you. So don't overthink a question. Try the obvious first. And if that's not working, then start thinking about it, right? But if it's pretty much already in front of you, then do it. We did that guy, remember you turned secant squared into its equivalent. Actually, I'm saying that the wrong way around. Isn't that one 5 tangents? Okay. Wouldn't you have to do something quite nice to 30? Tell me how you're going to tackle 30.
I would convert it to 2x to the 1/3 plus 5x to the 1/4 power.
And then distribute with the x. So you'd end up with 2x to the 4/3 plus 5x to the 5/4, and then the power rule. And remember to turn everybody back into weird 4th and 5th roots for style points. Would you agree that one is pretty obvious? X over 2, you know, it's just another way of saying a half x. So don't make your life hard. It's just a half x. So it's a 1/4 x squared when you integrate it. Yeah, we've done a 3 to the x. Antiderivative of that is 3 to the x over log 3. That's good to go. Don't need to do anything to that one. Remember we did this one earlier today, right? What's that guy? It is a standard integral. What is that guy?
One over the square root of 1 minus r squared.
And what's the antiderivative of 1 over the square root of 1 minus r squared? You're right, Ismail. You can't see it because it's tiny.
Inverse sine.
Inverse sine. Oh, that one we did. I almost screwed that one up, right? That one we've did. Hey, I am getting so good at that. 849.